So this is 33.10. So let's consider the circuit below. So in this circuit here, you have a voltage this way, and then you have a switch, and we have a resistor and an inductor. So this is a voltage delta V for the battery, and the switch here, let's see how this works. So this is B, and that's A, and we have a switch like that. So the switch can go to A or B. Okay, so this resistor is R, inductor L. Okay, so when the switch is in position A, so the battery drives a current. Okay, so in position A, the battery drives a current through the circuit. So there's a current going through like that, and ending up here. This current I is equal to the potential difference of the battery divided by the resistor R. In position B, the current is prevented from instantly stopping by inductor L. So this position will be shown this way, where you have your resistor again, you have your current. So the current is going to flow I. So current slowly dies due to the inductor. So the inductor will act to prevent the current from dying off suddenly. So it slowly dies due to the inductor. So let's look at what happens in the circuit. So the potential drop across the battery plus potential drop across the potential drop across the resistor plus potential drop across the inductor is equal to 0 by the loop rule. So we have the resistor R, inductor L, and then the potential drop across the resistor is given by Ohm's law. So delta VR is equal to current times resistor, and delta V inductor is given by the the EMF formula, which is L di dt. So if we take from what we learned in our circuit, if we take the current going across, we have the battery on this side, current going across the inductor is going to be negative IR, and then current going across the resistor will also be negative. So current going across the resistor is negative IR, current going across inductor is negative L di dt, and that's equal to 0. So this can be written as IR minus plus L di dt equal to 0. You can remove the negative sign if you want. So that's one option. So let's look at it this way. So we shall have di dt. So we shall have L over R. Actually, let's do hold on a second. Let me make sure I match it with what is in your textbook. So we shall have di dt equals minus I R over L, like that. And then we shall write di over I equal to minus R over L, minus R over L. So now we can integrate both sides. So integrating both sides gives you integral di over I equals minus R over L integral dt, and the current goes from initial current I naught to a final current I, and then in a time 0 to t. Okay, so the integral of 1 over I is a natural log of I naught I equals minus R over L times t, obviously from 0 to t, so that goes away. So we shall have a natural log I over I naught equals minus R over L times t. And if you take the exponent of both sides, then you're going to have I over I naught equals e raised to the power minus R over L times t. Or you can write I equals I naught e raised to the power minus R over L. Okay, so this just tells us that the current decays in an exponential way, where time constant tau is given by L over R. So what this tells us is that the current decays from an initial value I naught to a final value I in an exponential way. So we can draw the graph for this way. This is time, This is current, and it decays this way. Okay, where this is going to be I naught. Let me make this a little bit longer. So this is I of t, and I naught is right here. So that's your initial current. So it decays slowly over time, like that. And then I'll point out here, let me point out something here for you. So at the time constant tau, this is going to be 37%, so it's 0.37. So at time constant tau, this is 0.37 I naught. Okay, so remember we did this before with the capacitor. At one time constant, the capacitor, the decay will be 37% of the original. After two time constant, it's 13%, and it just goes on that way. So it needs at least 5 time constants to get to about 1% of the maximum. So that is the end of the chapter. Try the example 33.16 in your textbook. It's the same thing. It uses the same formulas that we've used or we've developed here. So try example 33.16 in the textbook. Okay. So that's the end of chapter 33.